I hope that everybody can see my screen right now, right? Just okay. Then I continue with the presentation. So as Dr. Bantana have already introduced about the talk of today, so I rather like to focus on the way that we use the technique so-called X-ray absorption spectroscopy, or XAS, which is quite famous for the synchrotron facilities, and also quite a useful technique for giving specific information and details on structurals and details on characterization that what we can get from the materials. So we use X-ray absorption spectroscopy techniques in metal-organic framework as well. But before I'm going to go into the details of what we use XAS for MOF, I firstly like to introduce a little bit in general what exactly MOF is. So we're starting with porous materials. So as you can see from this slide, there are many kinds and many types of porous material which you can think about. So it can also be a natural porous materials and also the synthetic porous material as well. And the size of the porous within the material is also can be varied, starting from mesoscopic size, macroscopic size, and even go down to the case of microporous materials, like what you can see from the case of zeolite and also metal organic framework, for examples. So the thing at metal organic framework is rather a new class of porous materials comparing to another type like activated carbons or porous nanofibers or even zeolite itself. Metal organic framework is basically combined two functions of the components, the main component within the structures. The first one is metal ion or metal clusters, and the second one is the organic linkers. So the combination between the metal cluster itself and the organic linkers forms the porous structure, which is a highly crystalline porous structure, so-called metal organic frameworks. And the combination between the two is coming from molecular cell assemblies by the coordination bonding between the metal clusters and the functional group at the organic linkers that and form the periodic structure of MOF, containing persistent porosities inside or void inside of the structures. So with this combination, you can somehow imagine about the structure of metal organic frameworks by thinking about the Tinker toy models. So at what I give a picture in this slide. So basically that what we can also try to change the metal node here into the design structure that what we want. So rather tight, various kind of metal cluster that we can use, and also the various kind of geometries of the metal clusters can be basically implement into the MOF structures. And another part is the connector here is belong to the organic linkers, that what we can see from this slide. Basically, we can also somehow functionalize the group at the organic molecule here, or even change the types of the organic linkers in order to construct the MOF structures to get the desired properties, so to say. So basically, MOF is rather can give you an opportunity to modular the construction. So basically, you can better decide which kind of metal you use and the organic linker you use in order to get the design MOF structures and what you want. And also with MOF is a porous material, which is a crystalline porous materials. So they have the confined space. Basically, you can somehow control pore size, channel size, and also the functionalities of the pore by changing the components and also control the topologies of metal organic framework that form. So since MOF is a combination between inorganic metal clusters and the organic linker itself, so that basically MOF somehow combine the characteristic of both parts into a unit. So they combine the rigidities and regularities from inorganic part with the flexibilities and responsibilities from the organic components, so that we can somehow get the both combination of the properties of MOF by the two components. Another part that since MOF is also the porous material, so basically we can somehow use MOF in two ways. So the first one is we use MOF as an intrinsic property of MOF, basically just use MOF itself and the functionality from all the components within the structures and the topologies and also porosities. Another thing that we can use is the gas-induced properties, meaning that we load some gas molecule inside of the porous of the MOF in order to behave some characteristic performance within the structures. So basically, we can somehow use both of the way to use MOF for various kind of application. So this slide somehow give you a little bit information about how we can apply MOF in the real world application, so to say. So it's starting from the beginning that we use MOF as porous material for storage and also the sensing device. And then we somehow implement MOF into the catalysis field. So basically, it's just try to control the active site within the confined space and within the periodic structure of MOF in order to get that high performance catalytic activities out of it. Another part, we can also somehow use MOF as a part of the device, so that we can also use MOF in optics and electronics fields in order to get the surface sensitive device that using MOF as the acting materials, for example, like a sensing part, and also the transduction of the signal by combining with some molecule, for example, like that. So considering it's about the way that we would like to use MOF in various kind of application, so we need somehow to consider back how to control the functionals and the properties of MOF. So basically, if you're thinking about the way to the origin of the function of MOF itself, it also depends on the physical and chemical property of MOF, which is related to the origin of control, which is the structure and composition within the MOF structures. And once we would like to use MOF in the real world application, or like, for example, like integrate into the device, we somehow need to think about the structuring and patterning of MOF or integration of the material with a part of the device before using it. So meaning that in order to get the exact property of MOF in the application, we somehow can control the properties in various kind of levels. So starting from the molecular levels at the structural and composition up to the point that we try to integrate it and in the part of the device itself. So here is some of the cartoon of the example that we somehow can design the components within MOF by changing the functionality of the organic ligand, for example, in order to get the exact properties that what we want. For example, like if you like to use for catalytic reaction to have the functionality that can enhance the catalytic performance, or even have the control of the size selectivities by using the different size of the organic ligand, for example, that we can somehow get the combination of these two kinds of MOF in the mesoscopic scale, like in this case, so to get the extractors by combining two MOF, we have the large pore inside behave at the storage part, and also the MOF will have the lowest porosity size or pore opening windows for the size selectivities, and on the top of that storage part, which is behave as the selective part in order to get only some molecule to store inside of the porous materials and leave some molecule with is bigger size or different functionalities or different characteristic properties out of the structures. Apart from that, MOF can also give you some idea of the different structure from what we get from the inorganic components. So basically, because of the combination of organic and inorganic part in MOF, we somehow can fine-tune the structure in order to get the properties so-called flexibles, the flexible MOF, so to say like this. So it can somehow show the structural change by external stimuli, like the addition of gas molecule that induce the structural transformation from large pore into the narrow pore, for example, like this, or even the induction by photos, like photos responsive and the thermal responsive as well. So with this is also another possibility that we can use MOF for various kind of application. For example, like we can somehow use this flexible MOF in the case of we would like to get the control duct release properties. So to get some at some specific external stimuli, we can store the target molecule inside of the pore of MOF. And once we put another stimulus that is induce the way to get the structural change, for example, change from the large pore into the narrow pore itself, then the gas molecule inside it release out of it. So basically this can somehow use as the smart material for drug release and drug encapsulation in this case. And also the way that we can somehow get into the detail of what the structure of MOF is required an in situ characterization and also the high performance characterization techniques, which mostly we also use the synchrotron facilities into the characterization methods of this kind of MOF. So here is another example that I would like to little bit point out, that flexible MOF can also give you information that basically that we can somehow control the responsiveness of material by the gas molecule that is specific target into the material. With this kind of properties, we somehow can apply this MOF for the sensing application. Apart from that, the selectivity of the absorption and release itself can somehow use to separate the different kind of molecule. For example, here in the case of mixed gas molecule of the hydrocarbon, the small size of hydrocarbon. So from this, we can somehow get the selectivity to store the acetylene inside of that flexible MOF compared to another kind of another functionality of hydrocarbon gas molecules. So thinking about the way that we use the techniques to study the structural information of MOF. So since MOF is crystallized, so the first the ideally method that you normally use to study the characterization of MOF, the characteristic of MOF is the X-ray diffraction techniques. So X-ray diffraction technique gives you information about the crystal structures, phase formation, and also the long range ordering within the MOF structures. So how the periodic structure that happens. So the distance between the metal node itself in the MOF and also the topologies and somehow of symmetry within the structures can be obtained by X-ray diffraction techniques. But if we like to get into the details of what happened in the metal node or the binding between the metal node with some specific organic ligand that we put in, and also some kind of target molecule that we would like to get into it. So X-ray diffraction may be not a straightforward way to get information like that. So this is the reason why that we also apply X-ray absorption spectroscopy techniques in order to study the local structures in the short range orderings of metal organic framework, especially at the part of the metal node or the metal clusters. So here is some of the cartoons saying that we have somehow get some defect structures within the metal clusters of the whole framework. With this, somehow can use X-ray absorption spectroscopy basically to focus on that metal part to get somehow extract on the information about the defect formation inside of the crystal structures. So the combination between X-ray diffraction technique and X-ray absorption spectroscopy technique give you a various of information that somehow can get into the detail on the mechanisms, how that MOF can somehow react with target molecules, or the MOF can be used as the active catalytic materials for performing with the high performance catalytic activities, for example, like this. So for the talk of today, I rather like to focus on the part that we use X-ray absorption spectroscopy technique with the work with metal organic framework. So I somehow give you like 4 of the work that we have done together with my colleagues during the past 3 or 4 years from this. So just to remind you a little bit on X-ray absorption spectroscopy. So basically we have 2 parts of the information that we can get from AGS. So the first one is X-ray absorption near structures, which rather more into the detail about the fingerprints, age position for the oxidation state, and also the symmetries within the structures. We also use this a lot of information from same region in order to identify about the way of how the local structure change in the symmetry within the metal node in case of metal organic frameworks. And also we use quite a lot of information on XRF part with its extended X-ray absorption file structure as well, in order to get into the details about coordination number and neighboring atoms around the target metals within the metal node in order to identify the active site and also the binding with the target molecule that we would like to get. So this is the first example that I like to mention is the analog structures of the famous MOF, which is called S-1 or the copper-based MOF, which is quite unique in this case and is quite applied in various kind of fields, so to say like this. So the way of this work is rather like to try to get the analog structure of copper S-1 by implement the highly sensitive metal clusters, so-called ruthenium, inside of the structure instead. So it starts from the synthesis of this. At the end, my colleagues also get this kind of MOF, which have the ruthenium cluster inside and resemble the structure of S-1, copper-based S-1. But the problem is with this ruthenium case, they somehow obtain that they get the mixed valence of the ruthenium pentavalent structure inside because of the starting material have the ruthenium core with the chlorine atoms as the chloride ion, so to say, as the binding site with the clusters. So at the end, basically they get the mix of the valence between ruthenium-2 and ruthenium-3+, which compensate by the chloride atom or the chloride ion, sorry, at the apical position at the ruthenium-3+. This one gives a drawback that you get the obstruct porosities of the ruthenium MOF because of the binding of that counter ion or chloride ion in this case at this apical position. So that it's quite a challenge that the way that we need somehow to improve the structures of the synthesis of to get the exact structure from this in order to avoid additional coordination by counter ions. In this case, it's a chloride ion here, and also give the so-called the coordination unsaturated sites or CUS, which is allowed to get another specific molecule to coordinate. For example, like the reactants material to coordinate at this part in order to use for catalytic performance. So the challenge of this kind of material that we need to find out the way to avoid additional coordination of counter ions and also enhance the catalytic activities and absorption properties of the ruthenium MOF with resemble structure of copper S-1. So that's come to the point that my colleague and I work together with this work that we somehow try to synthesize basically the analog structures of the ruthenium S-1 as well. But instead of having ruthenium-2 and 3 mixed valence, we somehow try to control to get only ruthenium-2+ inside of the metal cluster node. So with this, we use the control secondary building unit or CSA approach. So starting by using the preformed SBU, which already contain the ruthenium-2 inside of the structures, and then perform the MOF formation by exchange that binding ligand here with the organic linker that we want to get the structures, and at the end up with the ruthenium-2 S-1 resemble structures out of the formation. So if you can see from the XRD here, comparing with the previous work that obtained the ruthenium-2 3+, and also there's this work with the ruthenium-2 BTCs MOF, basically you get exact structures which have the same XRD patterns. But then come to the point that how we can somehow prove that our ruthenium is ruthenium-2 clusters inside of the structure. And this is the point that AKS come to play a role. So basically we use X-ray absorption near a structure or chain in order to identify the oxidation state of the rutheniums by probing at the ruthenium KH. So this work is basically performed at Delta Synchrotron facilities in Germany during our study in the PhD study, so to say. And from here, you can see from this graph that we plot the first derivative of the absorption coefficients at around the ruthenium KH. And we can somehow identify that inside of the MOF product is basically resemble the structures and resemble the pattern of the absorption edge with the SBUA prime here, which is the structure is look like this. we have the ruthenium-22 clusters inside. So I think I forgot to mention that this kind of SBU is somehow synthesized in the inner atmosphere. So in order to avoid the oxidation of the ruthenium-2 into the ruthenium-3, so instead of using the previous SBU in like this case, so with this at the end up with the formation of ruthenium-2 and 3+, we change to this kind of SBUs and perform the experiments in inner atmosphere in order to get the ruthenium-22 S-1 structures. And this one is having the open metal site or coordination unsaturated site, which allow you to get the coordination of the reactants into that ruthenium centers and can be used as catalytic centers for various kind of the catalytic performance later. So let's move to another example. So this one, that if you're thinking about the way that we can get, we get MOF with different kind of, so this is another example that we can somehow use MOF with the construction between metal clusters or metal ions with the same organic linkers, and it ends up with various kind of the structures. This kind of phenomenon is called polymorphisms in MOF. And also polymorphism is another material as well that you use the starting component with the similar chemical components, but links in the different spatial patterns. So basically depends on the synthetic condition, like the global concentration that you use, also the pH, and also the temperatures, of course, that also play a role in the packing efficiencies, and also the binding and the cluster formation end up with different kind of the structure. So in this slide is show you that if you use a trivalent metal ion, mostly is the chromium, iron, and vanadiums with 1,4-benzene dicarboxylic acid ligands or BDC, and you can somehow end up with at least 3 different kind of polymorphisms in MOF. So they have like basically 2 kind of this. We have the mu4O, mu3O clusters like this, and forming like a cage structures, which is called mu1O1 and mu88B, depending on the orientation of the cluster or the topologies that is formed at the ends. And if that kind of cluster is changed into the one-dimensional chain like this, it also can form another kind of MOF, which is called mu53, which is combining with the 1D chain channel that go through the structure like this and form the diamondoid porous frameworks of the mu53s. So with this, we can also use X-ray absorption techniques both in sand and exarc region in order to identify the mechanisms of the formation of polymorphisms inside of the mixed metal MOF, which is using chromium and iron together inside of the structures. So considering about in the details of characterization, so I will start with the X-ray absorption near structures at chromium KH, that we can see the difference between the case of using only chromium inside of the MOF and the case of using the mixed metals of chromium and iron inside of the structures. So in this case, we use 33% of iron as the starting point of the synthetics in all of the condition, and perform the reaction using microwave synthetics experiments with various kind of with different prolongation of the reaction times. So if you can see from the case of chromium, increasing of the reactions times from 5 to 250 minutes, basically we end up with more or less the same patterns of the chromium KH, like except at the case of the high numbers of, the prolongation of the reaction time, we see some tiny deviation of the pre-H structure at this case. But if you compare to the case of having iron inside, you somehow see the deviation that at the starting point, we see quite a huge pre-H at the beginning, and it getting decay at the prolongation of the reaction times. And also if comparing with the formation of the phase by XRD, what we can see that in the case of chromium's MOF, it's mostly from the mu101 structure, which is the cage-like structures like this, which is basically as the kinetic product, so to say, which is the having the mu3O cluster inside of the structures in most of the case, except the case that we have a prolongation of the reaction time of 120s and 240s. This one can form another phase of mu88B, showing that the deviation of these metal clusters and the tiny peak of the pre-age. But in the case of having iron inside, you basically see that they get the rather big pre-age peak at the formation of mu101. So meaning that some symmetry inside of that mu3O clusters of the mu101 get somehow deviation from the normal structure in the chromium case. So details about this will be discussed later on the Xray part. But then if you can somehow extend the reaction time up to 250 minutes in this case, that pre-age is vanished. And we found out that it is the formation of another type of polymorphisms, so-called mu88B and the mu53s inside of this product, together with the mu101, which is a kinetic product in this case. So if another consideration that if we go to the same spectra at iron KH of the mixed metals, chromium iron MOF, in this case, it's quite obvious that the pre-age is formed in all the case and with a similar patterns from all the case. So meaning that chromium and iron MOF basically have the mu4O structures that somehow get the structure distortion within the metal clusters. So the existing of pre-age represent the dipole forbidden of 1s to 3D transition in the non-central symmetric coordination. So if you consider about that mu4O structures, it's rather have the central symmetrics by the case of having chromiums or iron only with the oxygen atoms. But if the mixture between the two somehow give information that kind of the symmetries of the octahedral coordination is getting distorted. And this is the reason why that you somehow see the presence of the pre-age at the same regions. So here is some of the summaries about the case of chromium and chromium iron mixed MOF. So in the case of chromium iron mixed MOF, we see that distort octahedras inside of the clusters. And this is happened because of the incorporation of iron together with the chromium inside of the clusters. But if you get the prolongation of reaction time at 120 minutes or 240 minutes, this kind of pre-age is vanished because of the change of the structures of the polymorphisms from the case of distort octahedras in mu101 structures into the one-dimensional chain of mu53s, which is less structural distortion within the structure itself because of the highly oriented of the one-dimensional chain that we get at these structures. So insights into the details about the Xray part, we somehow can track back on the bond distance between the oxygens and chromiums in the case of chromium KH Xray, and also the bond distance between the iron and oxygens in the case of iron KH. And it somehow end up with the ideal information that have present the cluster inside of the structures as shown in this slide. So you can see that if only using a pure metals as a metal node in this case, we get basically the same distance between the oxygen bridge of 3 metals inside of the clusters with a similar distance. But if we change to the case of the mix, we somehow get the distortion of the distance in this case, that both of them is getting smaller in the distance because of the shrinkage, and in the case of forming the mixed metal clusters. But it's finding out that in the case of iron, the distance is getting lower than the one of chromium cells. This leads to the distortion of the metal cluster inside of the structures, and also the reason why that you can see the pre-age inside of the same regions. So this kind of the formation of these mixed metal clusters is possibly facilitates the facial phase transformation of chromium iron system, which is different from the case of the single chromium system. So this one is also the information that what we get that somehow can track back on the mechanism why we can somehow get the deviation of polymorphisms in size of MOF with having the same metal clusters and also the same organic linkers in the synthesis methods using the same kind of synthetic reaction using the microwave. But the different thing is just only the reaction time. So meaning that this kind of distortion of the crystal structures somehow can induce the change of one polymorphism with this kinetic product. In this case, it's mu101 into another more stable, more thermodynamically stable polymorph, so-called mu53 in this case. All right, and then we continue with another example that in the case of synthesis of highly porous nanocrystalline UiO66. So this UiO66 is another famous MOF which have been applied in various kind of applications because of the very high stabilities. But the problem is for the UiO66 to get the films of UiO66 coating on the surface is somehow not that straightforward way to manage to get the highly crystalline film with control orientation. So this is the reason why in this work we somehow try to optimize the synthetic condition in order to get the very high porosities UiO66 films. But starting from this, we somehow need to go back into the way of control the synthetic parameters in the case of bulk powder first, in order to get the parameters as a model to simplify what we get on the parameters for MOF thin film formation or the fabrication of that in the second step. So with this, we somehow try to grow the UiO66 by apply the control secondary building unit or approach or CHA approach, like what also presented in the previous slide, starting with forming the zirconium clusters. In this case, is the zirconium metacrylate cluster first, which have basically the same structure as the zirconium node within the UiO66 MOF, and then use the ligand exchange by putting the BDC ligand, the 1,4-benzene dicarboxylic acid ligand, to exchange with metacrylate linker here, and then form the periodic structure of UiO66 at the end. So we use AKS in the X-sub region in order to identify the formation of MOF together with X-ray diffraction techniques. So what we can see that in the case of using low amount of modulators and low amount of waters, so just only the metal clusters and the organic ligand itself is somehow forming the XRD is a broad spectrums. And also from AKS, you can see that the first shell is only one node here. But if we somehow adding up more equivalent of metacrylic acid, which is the coordination modulators, in order to somehow increase the crystallinities of UiO66 products at the end. So we end up with the XRF data at the zirconium clusters, which have the first shell, which is the size splittings of the first shell that observed in this case. So this is the phenomenon that explaining that in the case of using low ratio of modulators, we get basically the similar structure of the the zirconium metacrylate cluster itself. So from this, the distance between all oxygens to the zirconium is rather similar, and you end up with only one node here in the first shell. But if we put this kind of clusters into the UiO66 framework, this cluster is having a coordinated oxygen around the zirconium atoms. But when you put this kind of cluster inside of the UiO66 structures, each node is connected with 6 BDC linkers. So meaning that you get the local high symmetry orders of the clusters than the one inside of the crystal frameworks. So this is the reason why that you get the peak splitting at the first shells in this case. so that you basically end up with the two distance between the zirconium and oxygen bridge within the cluster itself, and the zirconium with the oxygen of the BDC linkers inside of the structures. And that's the reason why that you get two peaks in this case. So this is the one that somehow can also use X-ray absorption technique in the XRF region to combine with X-ray diffraction technique in order to identify the mechanism of formation of UIO66 by control SBU approach, using the zirconium metacrylic acid as the starting materials and also forming the UIO66 at the end. So, and last but not least example is we also use the same UIO66 material, but in this case, we somehow try to get the defect structures by adding up various number of the modulator inside and somehow produce the free coordinated unsaturated site of zirconium and the free hydroxy group inside of the structures of the defectives, comparing with the parent's defective free structure here. And with this case, it somehow can act as the active node for the catalytic conversion of D-xylo sugar into lactic acid products at the end. So, and it finding out that the case of control of the higher amount of defect structure inside of the UIO66 clusters, providing the free coordinated size of zirconiums and the presence of hydroxy group close to it. This one can somehow get the selective catalytic performance to convert D-xylose to lactic acid with high yield and also high selectivities over the another byproduct. This is called furfuros, based on the dehydration reaction from the sugars. So with this somehow can, I hope that the idea of what we present today is rather give you an information about the way that we somehow can combine the short range ordering characterization techniques in XAS together with the X-ray absorption, together with the X-ray diffraction techniques for the long range orderings in order to get some specific information about the structure of MOF. And we somehow can use XAS further into the details on the local structures of the metal cluster inside of MOF to get the detailed structural engineering, what we have tried to perform to get the defect structures and to get the preform SBU incorporated inside of the MOF itself, and also to probe the presence of catalytic active sites in MOF structures, especially at the metal cluster that what I have mentioned in the previous slide. And the last one, this can also somehow play a crucial role in the catalytic active sites in various kind of specific catalytic performance in this case. So I hope that at least this kind of information gives you the idea that what we can somehow combine synchrotron facilities with the chemistry on material itself. And thank you very much again for your kind of attention. And it's my pleasure to answer all the questions and discussion. Thank you.
Thank you for your talk. And I think now we can have questions from the audience. Is there any question from you guys? I check. Okay. Hi, Chris.
Hello, Antana. How are you? And hello, Suttipong, and lovely to see you all. I probably might have missed it halfway through, but some of your reactions were quite quick. So were you using quick XFs in your measurements? And is that what you were doing?
Okay, so basically we not perform the in situ monitorings or the operando XAS. So in this case, we somehow try to stop the reaction at a different kind of point and perform the XAS. So basically like ex situ studies. So because fantastic. Of our facility is not that fast of the measurements, it is one thing. So that's why we somehow try to get information into the detail that we can get the idea of how the mechanism formation of that MOF is look like. So very it's good. Rather in that way. So we also try to plan the in situ characterization as well, but still need due to the limitation of the facility that we have here. That's why we end up with that ex situ measurements.
That's fine. That's excellent. And the K range was quite useful anyway for the XF analysis. And you seem to get quite a good agreement on your structural determinations.
Yes.
It's a bit hard to see that in a set of slides, right, as opposed to tables and numbers and so on. But it looked like it was fairly good agreement.
Yes, thanks. So what and one thing to mention about it is that because of MOF is a crystalline material, so that's why we always correlate the data that what we get from AKS together with X-ray diffraction techniques. So at the end, that what we get information is all the information on the local structure from AKS and also the periodic structure from XRD. That's what we have. Yes.
Very good, thank you.
Do we have more questions?
Yes. Can I ask a question?
Sure.
Okay. Thank you very much for your nice talk. So I have a question, maybe not catch the point. So can you go to the page 12? So in the ruthenium based the MOF.
Okay, just a moment, please. So go back to screen sharing. This one, right?
Yes, yes. So as you can see, you use a precursor which contains the chloride, right? Then
yes.
you make the MOF, and the chloride. Does this chloride all leak out, or just something maybe remained? Because if you see the data below, you can see a little bit different, SBUA plus and SBUA, right?
Yeah.
So does this is the shadow peak is related to this this bonding?
Yeah. So I maybe a little bit explain on this. So we have basically two ways of the synthesis of this ruthenium S-1 MOF. So the first one that using the SBUA here, we have starting with ruthenium 2 and 2 in both cases. We have chlorine as a bridging between the clusters. And then from this point, if you use this one and put the ligand inside, and it end up with ruthenium 2 and 3. So still have some chlorine atom left that connect to the ruthenium 3. So that's why what you get from SBUA here is different from the case of the orange color of the ruthenium 2 and 3. So the orange and the red one is different. But if you change the synthetic procedure to SBUA prime in this case, which is the organometallic synthesis to get this kind of cluster inside of the argon atmosphere. This one is also starting with the ruthenium 2,2 as what we have in here, but without chlorine atoms inside. So basically from that pedal structure with the ruthenium 2,2. And then from that point, you adding up the ligand inside, and it's formed at the end the ruthenium 2,2 S-1 structures. So that's why the SBUA prime and the ruthenium 2,2 BTC showing more or less the same the same derivative of same patterns, comparing with the one with SBUA, which is deviate because of the synthetic procedure itself, change ruthenium 2 of one case into ruthenium 3 during the reaction.
I see. So can I ask why you this data is not do the fitting?
Sorry, again?
Can I ask why this data is not do the fitting? For example, go to the examples to see the coordination structure and the coordination number and the things.
All right. So what we have here is I would say that since this is more or less the work that we start to use XAS in MOF, so to say like this, because we are rather working with periodic structure. That's why we rather focus
5 years ago,
on the diffraction. So that's why at this point we somehow only like to confirm that the oxidation state is the ruthenium 2,2. So that's why we only focus on the same structures. And at that time, we still not that much, so to say that I don't have that much knowledge to do the exact fitting at that point. So that's why we end up with that what we have here.
Thank you very much. So last is the small question, like you use this MOF as a catalysis, right? So for some kind of catalysis reaction. So most of the case, such kind of catalytic list will be changed, the structure change. For example, this is something like reconstruction. So do you have any chance to see such kind of behavior in your MOF?
Okay, so we have another work which is not exactly what I present here. So the center is cobalt, and we somehow see the change during the catalytic reaction as well. But the most case that what we have observed is the coordination number is changed, and somehow once the starting materials or the byproduct or the product that get at the end is still binding to that catalytic active node. So we somehow get the deviation of the X half, not only about the coordination itself, but also the geometries because of the slightly flip of the structure inside of the periodic structures. That also what we have observed in the case of X half analysis.
That means the mass structure is still remain, right? Okay,
yeah, right. So the periodic structure is still the same, but since what I have mentioned in this work, so basically, maybe I go to this slide. So this one that we try to get the defective node inside of the periodic structures, but it's not all of the node have that defectives. So that's basically that we still maintain the periodic structure of MOF, but have only some part which have the actives inside. But still with this kind of Lego model, so to say, in this, you somehow can control the defective part to be periodic at some point, but not all the node. That is the thing. That's why we try to get the catalytic performance from MOF.
Yeah, I see. Thank you very much. Again, thank you, Watana-sensei and Abe-sensei. Thank you.
Thank you.
So we have questions from in the chat box. Can you open it?
Yes.
Yeah, from Tim.
Moment. In your final samples. So the question is, zirconium defect structure of UiO66 that you show reduce zirconium oxygen's coordination numbers or another way of characterization of the defect. Okay, so I think I may not going into detail that much about this. So basically what we do that we get the DFT calculation of the defective free node here, and also the defective node will have provide the zirconium cluster with have one of the linker missing as a model for the XRF fittings. And then from the signal that what we get from XRF analysis, this one we can get the combination between the percentage of the defect free and the defective node inside of the materials. So from that point, it ending up with the one which show high high catalytic active performance, having more components of the defective part comparing with another case. So basically we have two kinds of UiO66. The first one is the normal synthesis. We have a lot of defect structures, but another one we have the using modulators, we have more defect free structure inside, but still have the acetic acid as a capping agent. And once we try to remove that acetic acid out, they generate a lot of defective inside of that highly crystalline UiO66AA in this case. And from that, you get the highest performance of the conversion from sugar to lactic acid and high selectivity at the end. So more detail can also somehow go into that chemical combination paper in last year. I think they have another question, right?
Yes.
Structures. Okay, in the case of mixed iron and chromium MOF, we found that these structures and a shortage of FeO and chromium ores, right? How about the Fe valence? Okay, so in this case, if you can see, I maybe go that too fast in the talk, that you can still see the oxidation state is still the same. So in other case, same patterns, the different thing is only the pre-age part with related to the symmetries of the cluster inside of the structures, but then the oxidation state is still remain. So one thing to keep in mind that for this kind of polymorphism of MOF is rather belong to the trivalent metal ion inside of the clusters. Doesn't matter which kind of packing itself, but still maintain as a 3+. So we still see the deviation, the information that is still keep oxidation state into 3+, but only a tiny change. So one here is if you considered about this obtained model that after the fitting of Xray, you can see that the deviation of the shrinkage is only happened for the one which connect to the oxygen inside, which is the mu oxobridge oxygen. So the distance here is shortened, but the one with the organic carboxylate ligand is getting elongated. So at the end, you somehow compensate the crystal structure to be similar than what you get from mu101 structures. So XRD pattern still the same, but only a change of the deviation between the organic, the metal node is changed. Yeah.
Thank you very much. Thank you very much for your nice talk. And so for me, the 1.75 and 1.56 between iron and oxygen chromium bonding or oxygen iron bonding, I think it is very short. But you said that it is 3+, right?
Yeah.
So how about the bond balance? Did you calculate the bond balance?
No, in this case,
No?
not.
So I'm interested in that point. So please calculate the bond balance, and if it is satisfied, yeah, it is very, very interesting structure, I think. Thank you very much.
Thank you.
May I add something? Please go to slide number 15, please.
15, please.
Yeah, showing the same shape of your iron 3+, right?
Yes.
So to me, it looks very similar to iron in glass, silica glass structure. Yeah, so it is 3+. But from your Xray data on the slide number 16, yeah, the Xray structure in R space, it show the first shell, which is iron bonding to oxygen, right?
Yes.
Did you fit this one and get the connection number like a 6?
Yes.
Okay.
So basically, they have two types of the oxygen bridge. So this one is the first one, and another iron with oxygens to that. So they have iron with oxygen inside of the clusters with bridge 3 metals, and also the iron with oxygens that belong to the carboxylic acid from the BDC. So, but the distance is somehow getting deviation, so that get basically a broad peak here.
Okay. And what about the second, the higher shell? It looks to me like a real shell.
This one, right?
No, the next one,
This one.
Larger amplitude, yes.
Yeah. So I think
the magnitude, right? The magnitude, not
yes.
the real part or imaginary part, but the envelope.
Yes. So this is also the thing that what we get from the multiple scattering together with the one with this elongate of this. So that's why it's end up with that kind of big bump.
So that those are multiple scattering peaks.
Yes, from that two different oxygen here. So that's why you end up with, I mean, basically the multiple scattering is round about 3. That's what we get from the simulation from the model structures. And also the combination with that elongate of iron with oxygen in the case of carboxylic acid here. So that's why it's enough here. It's rather like a combination of that two.
Okay.
So, and this is only the detail, the information on the case of mixed metals. So it's not showing the, also for the one we have only iron is also different from what we get here. So that's why we get the information that, so we come up at the end that, okay, we sure that this is the mixed clusters, not a mix of these two clusters inside of the material. So the presence of both chromium and iron in the same cluster of the unit of MOF. Yeah. So just going back to this one, if I'm not wrong, this 2 peak is the standard patterns of the oxide compounds.
Yes,
yeah, so this 2 is a standard pattern, but this one is more from 1 to 6.
The pink one, I think the pink one is iron oxide.
Yeah, right. And also iron 2 and iron 3 oxide, exactly. So the last two.
Do we have more questions? So it's 5 minutes to 3 o'clock in Thailand.
It seems that time running fast, so,
Right.
and I hope.
Okay. Hitoshi.
Yep.
Yeah. Should we end the talk? Should we end the session now, as there are no more questions?
Okay, thank you. Thank you for a nice talk. And thank you for chair this session, Montana. Okay, next meeting 2 weeks later, we will have Professor Natori from Italy. So this will be also exciting seminar. So please come again to this Global Just Club, Europe and Asia Oceania. Yeah, thank you for coming everyone today. I'll see you 2 weeks later.
Thank you.